All right, so we're going to be going over the review for Chapter 8. Quick warm-up problem here. Feel free to pause the video and try any of these problems sort of in advance before I go over them, but I'm just going to be kind of going over them. So here we go. A boy is flying a kite. He lets out 150 feet of string that makes a 64-degree angle with the ground. If the string forms a straight line, how high is the kite above the ground? All right. I'm going to use some advanced artistic techniques here. We have a boy holding a kite. So here we go, kite. He says that the string is 150 feet and it forms a 64-degree angle with the ground. Now in this problem, we are kind of ignoring some things here. It's yeah, so like the height off the ground is not really discussed here, right? Because he's not holding it directly on the ground, I would assume. We're kind of fudging this a little bit, but we're just gonna assume it works. We are looking for this height here. We want to know how high above the ground the kite is. So we'll call that X. That will be our unknown. So this is an application problem. We had to draw this right triangle accurately to be able to go ahead and solve it. We are working with a 64-degree angles. This side over here would be our opposite side, and this is the hypotenuse. So to solve for the opposite, we need to use sine. That's unlike some of the application problems we looked at previously, but we can use any of the trig functions, sine, cosine, tangent. So we're going to set up a sine equation. Sine of our angle equals opposite over hypotenuse. We'll substitute in those numbers that we know. So the sine of 64 degrees is equal to x, which is our opposite side, the one we want to know, divided by the hypotenuse, which is 150. So this is the easier version, right, where we don't know the numerator. We just need to multiply both sides by 150 to solve for x. And I'm going to go ahead and perform this calculation. I'm going to just use it on my calculator, but you can use the Desmos Scientific. 150 times the sine of 64. I'll go ahead and show that calculation here on the screen. 134.8. On the quiz, I do believe I ask a couple different things. I either ask you to round to one decimal place or to the nearest whole unit. So in this case, we're talking feet. If this was a whole unit, we would round it to 135 feet. So that's how high above the ground the kite is. All right, let's go ahead and clear this and move on to the next one. We're going to review another trig application problem. All right. Again, feel free to pause this and do this in advance and then kind of check your work. So from the top of a vertical cliff 40 meters high, all right, so we have a vertical cliff, and it is 40 meters. The angle of depression to an object that is level with the base of the cliff. So there's an angle of depression. So we are looking, instead of looking horizontal, remember this is our horizontal, we are looking at an angle of depression, 34 degrees. Right, the angle of depression is relative to horizontal. We had to kind of look down 34 degrees to some sort of an object down here. We don't know what it is, something. And that object is on a level with the base of the cliff, so the ground, I guess, so to speak. All right, so we have this nice right triangle right here. So we got our problem, got our object, we're looking down 34 degrees at it, 40-meter cliff, so we're looking from the top of that cliff. And the only issue we have here is this angle is not inside of the triangle, but we do know that the horizontal sight line there and the ground in this case should be parallel, or at least so close that it doesn't really matter. And that means that the angle of depression looking down to the object should match the angle of elevation looking up from the object. So this angle down here, because those are alternate interior angles. That's going to help us solve this problem. So we are looking for how far the object is from the base of the cliff. So we actually want to know this side down here. So from the base of the cliff to the object, right? Yeah, that's the question we're answering. This is more similar to the ones that we did on the 8.4 notes. In this case, this is our angle. We know the opposite, and we are trying to solve for the adjacent. I mentioned in the 8.4 section that tangent is a pretty common problem for these because we often know or want to know the vertical and horizontal components, which are the opposite and the adjacent sides. And rarely do we actually know or want to know this sort of diagonal length, which is our hypotenuse. Anyway, we're going to be using tangent because opposite and adjacent. Tangent of our angle equals opposite over adjacent. So let's go ahead and sub in those numbers we know. Tangent of 34 degrees is equal to opposite over adjacent. And this one's the trickier one, so to speak. It's got the unknown on the bottom, and yeah, we can go ahead and multiply both sides by x to get it out of the denominator. So we end up with x times the tangent of 34 degrees is equal to 40. And then we have to divide both sides by the tangent of 34. Cancel out, and we'll perform that calculation over here to figure out what x is equal to. So I'm going to do 40 divided by tangent of 34. So I'm doing it on my calculator. You can see the calculations here. I get 59.3 approximately. Again, round to whatever place value the problem asks you to. I believe again on the quiz, I do ask to round to a whole unit. So 59, we look at the decimal place, it's 3. We'd keep that at 59. So we'd round our answer to 59 feet. In those cases, if it asks to round to the nearest foot or something. I do also ask you to round to a tenth or 1 decimal place, so make sure you know how to do both of those things. All right, and let's move forward. We're going to kind of bring it back to the beginning of the chapter where we were talking about the most basic stuff. Identifying trig ratios. So given a triangle, being able to write the sine ratio, cosine ratio, tangent ratio from a particular angle. These first 3, I'm going to go ahead and do all of these together because they all use the same angle in. So that'll allow me to label my triangle and just use that. So relative to angle in, we have our hypotenuse over here because it's always across from the right angle. Then we have the opposite side, which is across from the angle that we're going to be using for our trig function. And then we have the adjacent side, which is the leg that's next to it. And so there we go. We should be able to write all of our trig ratios based on this labeling. So sine is equal to opposite over hypotenuse. So 12 over 15. We could leave it like this, but this ratio does also simplify. So 12 and 15 are both divisible by 3. So we can make that 4 over 5. You can reduce it or not. It doesn't actually matter too much, but I'm going to go ahead and reduce them as I go. All right. And then cosine is adjacent over hypotenuse. So that's 9 over 15. Again, that does reduce. So we'll go ahead and reduce it here. Both divisible by 3. So we get 3 over 5. It's fine. And then the last one is tangent. We're doing opposite over adjacent. So 12 over 9. And so these are the ratios here. Again, this one reduces, again, divisible by 3. So that's going to be 4 over 3. So those are all of our trig ratios relative to angle in. I'm going to go ahead and erase the labeling on my triangle because the next 3 all use angle P. So I want to go ahead and label relative to angle P. So that's one over here. My hypotenuse does not change, right? That's always there. No change on that. But now this side over here is the opposite. It used to be the adjacent for n. For n, it's next to it. For p, it's across from it. So there. And then we have our adjacent side here, the 12. Again, that's similar as before, right? This used to be the opposite for angle n. So the opposite and adjacent switch, that's really all that happens when we change the angle we're using. Anyway, sine of p is going to be opposite over hypotenuse, which is 9 over 15. We already saw that that actually does reduce here. It's the same thing as cosine of n. That reduces to 3 over 5. So 3, 5. Yeah. Okay. Cosine of p, that's adjacent over hypotenuse. That's 12 over 15, which again reduces to 4 over 5. And the last one, tangent of p, opposite over adjacent. That's 9 over 12, which reduces to 3 over 4. So something I do want to turn your attention to as we're looking at these, notice which ones of these are the same. So the sine of n is the same thing as the cosine of p. That's because of that switching of our opposite and adjacent, right? For n, we were doing the opposite over hypotenuse. But relative to angle p, that's the same thing as doing adjacent over hypotenuse. So those sine and cosine values end up being the same. And then cosine of n is the same thing as sine of p. Same idea. It's because the opposite and adjacent switch. So when we're doing here, cosine of n, we're doing 9 over 15, but that's opposite over hypotenuse. That's sine for angle p. Anyway. And then tangent is sort of similar. Tangent doesn't use hypotenuse. It only uses opposite and adjacent. So when the opposite and adjacent switch, it just actually flips our fraction to its reciprocal. So instead of 12 over 9, we ended up with 9 over 12 because the opposite and the adjacent switched. Anyway, just knowing which ones are the same when we kind of switch the angles, that's kind of an important idea as far as trigonometry goes. All right, let's go ahead and move forward. Now we're going to talk about solving for an unknown side length. We end up with kind of two types of these problems. It has to do with which part of our ratio is the unknown, right? Whether the unknown is in the bottom and we have some number on top, or whether that's flipped. It just sort of changes the solving just a little bit, and we'll see one of each of these. So let's go ahead and solve this problem, and I'll kind of talk through my process. So we have a 59-degree angle. I want to label my triangle relative to that known angle. So we have our hypotenuse down here. That's always across from the right angle. Then we have the opposite side and the adjacent side. So once we label the triangle, we choose the two sides, the one that we know and the one that we want to know. And that tells us which trig function to use. Adjacent and hypotenuse, that goes with the ka part of SOHCAHTOA. Adjacent and hypotenuse, that tells us to set up a cosine equation. Cosine of our angle equals adjacent over hypotenuse. So that's the equation format we'll be using, and we'll substitute in the things that we know, which is cosine of 59 degrees is equal to adjacent A, which is 34, over hypotenuse, which is our unknown. So, like I said, there are two types of these equations, and it boils down to which of these in our ratio is unknown, whether it's the denominator like this one or the numerator, like I think we'll see in the next example. So in this case, when your denominator is in the, when your unknown is in the denominator, it takes an extra step. We have to get it out of there. We multiply both sides by x. So we have x times the cosine of 59 degrees. It's equal to 34. And then we have to divide by the cosine of 59. We keep it in this sort of exact format until the end. We don't, cosine of 59 is just going to be some number, but it's this long, non-terminating decimal. It just keeps going on. So we keep it exact here so that we don't round too early. We just work with it as this sort of abstract idea of the cosine of 59. And now we have to perform a calculation. So now we need to use our calculator to figure out how to calculate this. So you can use the Desmos Scientific, punch that in, or I'm going to go ahead and do it on here. 34 over cosine 59. If you're not sure how to use the calculator on this, you can go back and watch the video on 8.2. That should help you out. So I got 66.0. For these problems, I believe on the quiz, I do ask you to round to one decimal place. So in this case, it was 0.0. I don't actually have to write that part. I can just leave it off and make it 66 if it's 0.0. Anyway, moving on to the next one. All right, so here is another right triangle, and we are solving for the side RQ with the X on it. Again, same idea. We're going to pick our angle. So the angle is this one that we know, and label my triangle relative to that. So in this case, I know my hypotenuse. This side over here is the opposite, which is what I want to know, and this side down here would be the adjacent. So we pick our trig function based on the two sides the one that we know and the one that we want to know. So opposite and hypotenuse, that goes with sine, the SO part of SOHCAHTOA. So we got to set up a sine equation. Sine of our angle equals opposite of hypotenuse. We substitute in the values that we know. So our angle is a 24-degree angle, and opposite is x, so that's the unknown on top, and the hypotenuse is 16. So this is a little bit easier. The unknown is in the numerator. The only thing we'd have to do to solve this is get this 16 out of our denominator. So we multiply both sides by 16, and that's it. That's all we're going to have to do. We just need to use a calculator here to figure out 16 times sine of 24. So I'm getting this answer right here, around 6.5 approximately. And I'm going to round to 1 decimal place. Again, follow the directions as far as rounding goes. 1 decimal place, 2 decimal places, whatever it asks you to do. So here we go. That's our answer. And I'm going to go ahead and stop this right here and pick up in a part 2. See you guys later.